This short video is about Diffie-Hellman key exchange, part 1. You can use the analogy of a lock and a key to explain how encryption and decryption work. When you encrypt data, it's like putting it in a box and then locking the box. And when you decrypt data, it's like using a key to unlock the box. Imagine a situation where two people, say Alice and Bob, have a secret. The secret is locked in a secure box, but Alice and Bob are not in the same location, and it's difficult for them to share the key so that they can both access that information without somebody else having access to that key. So what can they do in this kind of situation? Now, in real life, the keys that we're talking about are in fact numbers. And around 1975, Ralph Merkle proposed a solution to this type of problem, and it was later named after American cryptographers Diffie and Hellman. The idea is that Alice and Bob could generate a shared, secure key even if they were in different locations, and they did not have a secure line that they could communicate over. So let's look at how that can be done. So, first Alice and Bob agree on two numbers, P and G, and these numbers are not secret, and they can communicate about these numbers over an insecure line. But then Alice and Bob both choose secret numbers. They do not share these secret numbers with anybody. So in this case, Alice uses her secret number, A, and calculates G to the A, small a, mod P equals capital A. And Alice sends the results of this calculation. She sends the capital A to Bob. And then Bob does the same thing. So Bob uses the P and the G that Alice and Bob publicly agreed upon, and then he uses his secret number, small b, and he calculates capital B equals G to the small b mod P. And he sends the results of the calculation to Alice. So Alice receives B, and Bob receives A. Now remember, they send those calculations over an insecure line. Anybody can listen in. But then Alice calculates S equals B raised to small a mod P. So she's using her secret number A that nobody knows, and she calculates S. And Bob does the same thing. He calculates A raised to small b, his secret number, mod P, and that equals S. And then the interesting thing is that the S that Alice and Bob calculate are in fact the same number. And this S is the secret key that they use to decrypt data. And they also use it to encrypt data. So let's look at how this S can actually be the same number. So on the left we have Alice, on the right we have Bob. So we call that S Alice. So S Alice equals B to the little a mod P. S Bob equals A to the B mod P. Now we substitute B and A. So capital B was equal to G to the B mod P. And capital A was equal to G to the A mod P. Now, because of the rules of mod, G to the B mod P raised to A can be simplified and is equal to G to the B raised to A. And we make that simplification on the right side too. Now, because of the rules of algebra, we can say g to the b raised to a is equal to g to the b times a. We do the same on the right-hand side. And by the rules of arithmetic, g raised to b times a is equal to g raised to a times b. So we can see that S Alice is equal to S Bob. Now, it's interesting that Alice and Bob could share the results of their calculation, the capital A and the capital B. They could share those numbers over an insecure line. So you would wonder, couldn't an eavesdropper calculate Alice and Bob's secret number by doing the calculation in reverse, so that they could find little a from capital A and little b from capital B? And it turns out that this is not so easy. That computing little a from capital A is much more difficult than computing capital A from little a. And all of public key cryptography is based on functions of this sort that are much easier to evaluate in one direction than they are in the other. And here's an example of a P and a G that might be used in real life. So P, it's a prime number. You can see it's pretty long. And G. And thank you for listening in.